So now we'll see the definition of linear transformation. The definition is let V and W be any two subspaces. V and W be any two subspaces over the field F. Here field contains scalar, all scalar points, and a mapping T from V to W is called a linear transformation. If small v1, v2 belongs to V, here V is vector space, then transformation T of v1 plus v2 which is equal to T of v1 plus T of v2. First condition. In second condition, for all A belongs to F, A is a scalar. That's why it belongs to field F, and V belongs to vector space. V belongs to vector space. Then the linear transformation of this T of AB is A into T of B. In other words, combining these two conditions, we write in one equation, that is T of A into V1 plus A into V2, which is equals to A1 into T of A1 V1 plus T of A2 V2, which is equals to A1 into T of V1 plus A2 into T of V2. Here A1 and A2 are the scalars which belongs to the field F. Therefore V1 V2 which belongs to the vector space. This is the linear transformation definition. Okay, we will see one example which is appeared in model question paper. What is the problem? The example is let I from mapping from B to R be the integral mapping, that is the integral mapping, that is I of V which is equals to integral 0 to 1 V of t into dt. Show that I is a linear transformation. I is linear transformation. Shortly write it as LT. Linear transformation. First we have to check whether if take two U and V spaces, subspaces, we take let R first one for all U comma V belongs to capital V vector space. That first one is T of V1 V2. Here we are taking U and V. T of U V. T is here I of U V. I of V is given integral from 0 to 1 V of t dt. Therefore, I of, we take these two subspaces, we get I of u comma v, I of u v which is equals to integral 0 to 1 u of t plus v of t. U plus v, here plus u plus v, integral from 0 to 1 u of t plus v of t whole thing into dt, which is equals to integral from 0 to 1 u of t dt plus integral from 0 to 1. We are splitting the integral for both the functions v of t dt. We give here given what is I of v is v integral from 0 to 1 v of t dt. Integral from 0 to 1 u of t dt, which is nothing but I of v. I of v plus this is I of u, this is I of v. I of v integral I of v which is equal to integral 0 to 1 v of t dt. Therefore, this is I of v. Therefore, I of u plus v is, we get I of u plus I of v. In second, we have to check whether this is equal to this. For all, consider for A belongs to the field F and V belongs to the vector space. Consider T of AB means here given I of V. I of AB which is equals to integral from 0 to 1 A into V of t dt. Okay. Using this, we write I of AB, which is equals to integral from 0 to 1 a into v of t dt, which is a is outside the integral, because a is a scalar here. Therefore, the integral from 0 to 1 a into integral from 0 to 1 v of t dt. What is v of t dt? Integral from 0 to 1 v of t dt, which is nothing but I of t. Therefore, a into I of t. Here, LHS I into AB, which is equal to a into I of t. Here a is scalar, which belongs to the field. Okay. Therefore, these two conditions are satisfied. Therefore, this is the given mapping is linear transformation. Therefore, I is linear transformation. Therefore, understood? So now we will solve one more problem on linear transformation. Let I is a mapping from VR to V to R. Be a mapping, this is a function fx which is equal to 3x comma 5x. So that f is linear transformation. Okay. First one, linear transformation. Given function is fx is equal to, given function is fx equals 3x comma 5x. 3x comma 5x. Okay. Let x1 to find, to check whether one is holds good or not. The condition one is holds good or not. x1 comma x2 belongs to the vector space V, and then the f of x1 plus x2, which is equals to 3 into x1 plus x2 comma 5 into x1 plus x2. Therefore, 3 into x1, we multiply 3 inside the bracket, we get 3x1 comma 3x plus 3x1 plus 3x2 comma 5x1 plus 5x2. Therefore, we get here we are adding two functions. Therefore, we are splitting that into two functions. Therefore, 3x1 comma 5x1 x1 as it is, and plus 3x2 comma 5x2. Therefore, 3x1 5x1 here 3x 5x, this is fx. In place of x, here we have x1. Therefore, fx in place of fx we write f of x1 here, plus in this place we write f of x2. Therefore, LHS is f of x1 plus x2, which is equal to f of x1 plus f of x2. First condition is holds good. Then in second condition is, for second condition we take one scalar a which is equal to, which belongs to the field here, and that x is belongs to V. Therefore, V here V. Therefore, f of x is 3x comma 5x. Here we take that f of ax is what? F of ax is 3 into ax comma 5 into ax. We take a as common outside the bracket, get a into 3x comma 5x. Therefore, a into 3x comma 5x is f of x. Therefore, f of ax which is equals to a into f of x. So both conditions 1 and condition 2 are holds good. Therefore, the given function f is linear transformation. Understood? This is the easy problems. So now we will solve one more problem on linear transformation. Show that the transformation f from V to R to V to R defined by f of x comma y, which is equals to x plus 6 y plus 2 is not linear. We have to show that this is not linear. For this, consider first condition, which is f of x1 plus x2 y1 plus y2. For x, we take for x1 and x2. For y1 we take y1 and y2, y1 plus y2. Therefore, x1 x2 comma y1 y2, which is equals to, by using this we get x1 plus x2 plus 6, x1 plus x2 plus 6 comma y1 plus y2 plus 6, 2, y1 plus y2 plus 2. In place of y, we have y1 plus y2. In place of x, we have x1 plus x2. Therefore, by using this function, we write x1 plus x2 plus 6 and y1 plus y2 plus 2. Here, the equation, we call this as equation 1. Then, consider f of x1 f of x1 comma y1, split these two, x1 comma y1 plus f of x2 comma y2. This is LHS of first condition, this is RHS of first condition, which is equals to f of x1 comma y1. Here x1 is nothing but x. Therefore, x1 plus 6 comma y1 plus 2, y1 plus 2 plus f of x2 y2, which is nothing but f of x1 x2 y2. Here in place of x2, here we have x, and in place of y we have, in place of y2 we have xy. Therefore, f of xy is this. Then f of x2 is f of x2 comma y2 is f x2 plus 6, x2 plus 6 comma y2 plus 2. Add these two, we get x1 plus 6, x2 plus 6, x1 plus 6 plus x2 plus 6 comma corresponding first element with first element, and y1 plus 2 plus y2 plus 2. We get x1 plus x2 plus 12 comma 6 plus 6 12, y1 plus y2 plus 4, 2 plus 2 4. Okay. Therefore, this is equation 2. Call this as equation 2. This is LHS. LHS, what is this? Is LHS of equation 1. This is RHS of the condition 1. Therefore, we get equation 1. If this is LHS, RHS means these both are equal. But here equation 1 and 2 are not equal. Therefore, condition 1 is not satisfied. Therefore, equation 1 from equation 1 and 2 both are not equal. From 1 and 2, one is not equal to 2. That is f of x1 plus x2 comma y1 plus y2, which is equals to f of, which is not equal to f of x1 comma y1 plus f of x2 comma y2. Therefore, equation 1 not satisfied here. Therefore, f is not a linear transformation. Linear transformation. linear transformation. These three problems enough to understood. Enough. Therefore, in continuation that, what is kernel? Kernel let T with the linear transformation from V to W. V to W, here V and W are subspaces, and there is kernel of T. The kernel of T, that is kernel we denote KER of T, kernel, which is equals to V belongs to V. Here V is subspace, here capital V is vector space. T of V is 0. That 0 belongs to the subspace W. 0 belongs to subspace W. This is the kernel definition. And also the image of T. Image of T we denote img of T, which is equals to W belongs to vector space W, capital W. Here this is vector space. Here this is small w is subspace. That is equal to W belongs to capital W, which implies W equals T of V for some V belongs to V. Here V is small subspace. The capital V is vector space. And the rank of T is dimension of the image of T. Here rank of T is equal to dimension of the image of T. Dimension of the image of T. And the rank of and nullity of T is nullity of T. The nullity and these two are further studied in the rank nullity theorem. Therefore, nullity of T is kernel of T. Dimension of kernel of T. Dimension of kernel of T. This is the kernel and the image of T. Okay, the rank of T, which is equal to dimension of image of T, and nullity is equal to dimension